Hi, we're gonna move on to chapter 9. So, the first part is ANOVA, analysis of variance. ANOVA is the one of the classical techniques in statistics. So, the data, suppose that there are A independent groups. So, group can be uh, blood type, okay, for example, or major, right? If it's a student and then math major, physics major, things like that. So that could be another example of group. So anyway, for each group, we obtain B independent observations, and so we use Xij, a realization of a random variable X for the J's repetition at group I. Okay, so and we assume that this Xij follows the so this is the group mean, right? For group I, and this is variance, and these are mu1 and mu a and sigma squares are unknown parameters. And we have data set, so we have a data set. This is data I equal to 1 to A, J equal to 1 to B. So we have the sample size is A times B, and we are interested in testing whether there's a, so this one is what, no difference among group means, right? So we should to test whether there are significant differences in the group means or not, right? So okay, so how can you do likelihood ratio test? Where first the parameter zeta is mu1 2, so a plus 1 dimensional, and parameter space is omega is just unrestricted. There's no restriction, but omega null has a restriction, right? So this is the restriction imposed by from the null hypothesis. Okay, so because the null hypothesis is equal mean, so that's why we have this restriction imposed in omega null. So likelihood function itself is this form under this model assumption normal, right? So under normality, we can easily derive this likelihood function, and then MLE. So how to find the MLE? First, we maximize. We find mu hat I by maximizing the this function, which is minimizing this function, right? So minimizing this function. So for each I, right? So this one is obtained by minimizing j equal to 1 to b xij minus mu I square, so which is basically the sample mean of xij in group I. And sigma hat square is the once you plug in, so this one is mu I hat, then maximizing. So you plug in mu I hat first, and then the likelihood function is now function of a sigma square, and so you can easily find the maximizer of the likelihood function as a function of a sigma square, and maximizer over sigma square, you get this one. All right, and we can do the same thing under the null hypothesis. So under the null hypothesis, we have a restriction. So the parameter restriction is this one. So we have only one parameter. So here the mean parameter is only one parameter instead of a different parameters. So this one is basically we now have a restriction mu i's are all equal. So the mu I hat are all equal to mu hat, which is minimizer of what? Double summation xij minus mu square. So that is this one. And then this one is mu I hat, right, under the null hypothesis, and then we get this MLE. And so the likelihood ratio test statistic. So then basically the ratio between the two is essentially becomes the, so this one is what, 2 pi sigma 0 square hat minus 2 over AB times exponential, right? Minus 2 over AB. And denominator is square minus 2 over AB times exponential minus even 2 over AB, something like that. So basically you can see that the ratio actually they cancels to each other, and the only thing is 2 pi cancels, and so the only thing left inside is just the ratio of this variance component, and you can actually so obtain this. I'm gonna explain why in the next page, but anyway, once we derive that, then we want to we reject if this ratio is less than k for some k, which is equivalent to for this term greater than some k, some c. So why we have this equality, this second equality? Well, basically this is because the sum of squares. So sigma hat, okay, sigma hat square is what? 1 over AB SST, right? Because sigma, I'm sorry, sigma hat is actually this one. So SS within this one, right? And sigma hat null square is 1 over AB SST. So here the ratio is what? Sigma, denominator is sigma hat square sigma hat 0 square minus 2 over AB. So that means you basically have AB cancels out, and SS within over SST. But we can show that SST is SSB plus S. So 1 plus SS within plus SS between, because of this. Okay. Well, why we have this SS decomposition? Because we can just always subtract the mean and add the mean, right? Here. So if you include this part and then expand the squares, then you have this decomposition. Okay. So the only thing left with is to compute the ratio. So the finding the sampling distribution of this ratio, because this is the ratio, right? So turns out that this one follows. We can show that. We'll show that this statistic follows F distribution with degree of freedom b minus 1 Oh, I think this is A. Okay, and I think I probably need to fix this. So okay, let me stop here and then we'll continue.